That feeling of being overwhelmed by information, it's almost a constant now, isn't it?
It really is.
We're just bombarded with text, images, videos,
Mhm.
this tidal wave of unstructured data.
Yeah, and finding what you need is tough.
And the old ways of searching,
Yeah.
just looking for exact keywords, they feel increasingly inadequate.
Absolutely.
You search for a smartphone, right? But what about cell phone or
Wow.
mobile device? You're instantly missing a whole range of related ideas.
You miss the concept. It's like trying to understand the ocean by only looking at the water molecules, not the currents or the ecosystems, like you said.
Exactly.
What's really transformative here, I think, is the shift from that literal keyword-based understanding to a conceptual one. Traditional search just looks for exact matches.
Right.
But how we understand things, it's rooted in meaning. And the sheer volume of this unstructured data has just starkly highlighted how limited that old approach is.
So vector databases come in here.
Exactly. Vector databases offer a fundamental change. They are engineered to grasp the meaning behind all this data.
Okay, and that's the core of our deep dive today then. We're diving deep into vector databases, which aim to understand the essence of unstructured data. Imagine being able to translate text, images, audio, whatever, into a shared language that a computer understands. Not through exact words, but through underlying concepts.
And they do this using these high-dimensional vectors.
Right, representing data as these vectors. It's like moving from identifying a fruit by its label to, I don't know, understanding its characteristics, its sweetness, its texture, its nutritional profile.
Okay, let's unpack this idea of high-dimensional vectors a bit. Imagine describing an animal, say, a dog.
Okay.
You could list features like its size, its breed, its typical behaviors, right? Now, imagine turning each of those features into a number.
Right, a list of numbers.
A vector database does something kind of like that, but with like way more abstract features that are inferred by machine learning models.
Okay, so not features we necessarily pick out ourselves.
Probably not, no. These models analyze your unstructured data text, images, and they identify hundreds, maybe thousands, of these hidden characteristics. And they represent them as this long sequence of numbers that's your high-dimensional vector.
Wow, thousands.
Sometimes, yeah. And the key insight is that each dimension, each number in that sequence, captures some subtle aspect of the data's meaning, even if we can't easily put a label on it.
So instead of simply registering this article mentions climate change, it's capturing the underlying concept of climate change, maybe its causes, its effects, related science, different viewpoints, all encoded within that vector.
That's the goal, yeah. All encoded in that geometry.
And the real power emerges because representing data this way allows us to search based on conceptual similarity.
Precisely. This capability, similarity search, that's the central advantage of vector databases. Instead of asking, does this exactly match my keyword, you're asking what in my database is most conceptually similar to my query.
That sounds revolutionary for navigating all this complex information where meaning is often, implied rather than explicit.
It really is.
Now, this isn't just theoretical, right? Vector databases are the engine behind a lot of cutting-edge AI applications. And one of the biggest is Retrieval Augmented Generation, or RAG.
Yeah, RAG is huge right now. If we connect this to the bigger picture, think about large language models, LLMs. Everyone's talking about them.
Right.
They're amazing at generating text, but their knowledge is, well, inherently static. It's limited to their training data.
Which could be months or even years old.
Exactly. And they can also be prone to inaccuracies, hallucinations, they call them, or they just lack specific up-to-the-minute info. It's like having a brilliant encyclopedia that can't be updated.
Right. So RAG is like giving these LLMs a dynamic, constantly updated external knowledge source to check before they generate a response.
Perfect analogy.
And the vector database acts as this incredibly efficient and semantically aware library that the LLM can draw upon.
Which brings up a crucial question. How does R actually use a vector database? The basic idea is that before the LLM writes its answer, the RGAE system first pulls relevant bits of information from an external knowledge base.
Like the library you mentioned.
Exactly. And the vector database is what makes that retrieval possible, based on the semantic similarity between the user's query and the knowledge stored in there.
Okay, so the mission for this deep dive is clear. We're going to thoroughly explore the inner workings of vector databases.
Get right into the nuts and bolts.
Yeah. We'll look at how they transform raw, unstructured data into these meaning-rich vectors. We'll delve into the mechanisms they use to store and search through these vectors really fast.
The indexing part.
Right. And we'll understand precisely how they function as this essential memory for RGA systems, making our AI systems more informed, more dependable.
Sounds good.
Okay, let's unpack this initial step then. How do we turn raw data into these vectors? The embedding process.
Right. The transformation process relies on what we call embedding models. These are pretty sophisticated machine learning models, often deep neural networks.
Okay.
They're trained on massive data sets to basically discern underlying patterns and semantic relationships. They learn to map your text, your images, or other data into this continuous high-dimensional vector space. Think of it like learning the hidden code that represents the meaning of information.
Like, okay, consider different musical instruments. You could describe them by their shape, materials, the sounds they make. An embedding model does something similar, but it learns these subtle characteristics automatically from the data itself.
Exactly. For text, the first stage is typically pre-processing, cleaning the text, breaking it down into meaningful units, often words or subwords, tokens.
Tokens.
Yeah.
Yeah.
So for text, you might remove like common punctuation or maybe words that don't add much meaning, stop words.
Like the or a.
Exactly. These tokens are then fed into the embedding model. And there are various types of these models, some like Word2Vec, Glove, Fast Text. They're designed to create embeddings for individual words.
Okay.
They learn that words frequently appearing in similar contexts tend to have vector representations that are close to each other in the vector space. The key idea there is that meaning often comes from the company words keep.
So words like happy and joyful would have vectors located near each other in this space because they're used in similar ways.
Precisely. But then you have more advanced models like BERT, SentenceBERT, Universal Sentence Encoder. These are context-aware.
Context-aware.
Meaning they understand that the meaning of a word can change depending on the surrounding words. So the word apple in apple pie is different from apple ink.
Okay, so they'd get different vectors.
They would get different vectors, yes. This contextual understanding gives you a much richer, much more accurate semantic representation.
That's a crucial distinction. Huge difference. And this process isn't just for text, right? You mentioned images.
Correct. For images, we use models like convolutional neural networks, CNN, you might have heard of ResNet or VGG, and more recently, vision transformers, or VIT.
Okay, CNNs and VIT.
The big breakthrough with CNNs was their ability to automatically learn hierarchical features in images, starting from simple edges and textures, building up to complex objects and scenes.
So it learns what's important visually.
Kind of, yeah. It means the resulting vector truly captures what is visually meaningful, which leads to much better image similarity search than just comparing raw pixel values. These models analyze the visual elements and encode them into a vector.
So two photos of the same landmark, maybe from different angles or in different lighting, would ideally have vectors that are closer to each other than a picture of a completely different landmark.
Ideally, yes, that's the goal. And then we have these incredibly powerful multimodal models like CLAP.
CELIP.
Yeah, CLAP can embed different data types like images and text into a shared vector space.
Oh, okay, shared space.
Yeah, it's a profound development because it lets you perform searches across modalities. You could, for instance, find images that match a textual description.
Like searching for a cat sitting on a windowsill and getting actual cat pictures, even if the words aren't in the image file name or anything.
Exactly that, even without metadata matching.
That's staggering, that capability. So after all this intricate pre-processing and applying these sophisticated models, we get this high-dimensional vector, this long sequence of numbers. And each number, each dimension, represents a latent feature the model inferred. Not necessarily something we can easily label, like color intensity, but collectively, these dimensions capture the core essence, the meaning of the data.
You got it. And this leads us straight to the fascinating concept of the geometry of meaning. These high-dimensional vectors exist in what we call a vector space. And within this space, the proximity and orientation, how close they are and which way they point, directly reflect the semantic similarity of the original data points. Things with similar meanings end up with vectors close together in this space. It's like mapping out the conceptual landscape of your data.
So going back to our initial example, the vector for car and the vector for automobile would be really close in the vector space, clustered together.
While the vector for banana would be much further away. And this works even for those related but not identical terms like vacation, holiday, getaway. Their vectors would cluster together.
They should, yes, in the same conceptual neighborhood. This is the fundamental shift, moving from matching surface-level words to understanding the underlying ideas.
That's the power of semantic search. It's not about finding exact keywords. It's about finding items that share a similar conceptual core.
Exactly. And like we touched on, the evolution of embedding models from context-agnostic ones like Word2Vec to these advanced context-aware ones like BERT that's dramatically enhanced the accuracy and richness of this semantic space. Right, allowing for much more nuance.
Way more nuance, much better at handling ambiguity, like the different meanings of bank, riverbank versus financial bank.
So it really sounds like the quality of these initial embeddings is absolutely critical. It's the foundation for the whole thing, right? The vector database search, any RAG system built on top.
Absolutely paramount. Garbage in, garbage out, as they say.
Yeah.
If the embeddings don't accurately capture the meaning, the search results won't be relevant.
Okay. But these high-dimensional vectors, while they're great at capturing meaning, they also bring challenges, don't they? Primarily because they're so high-dimensional.
They do. That's the flip side. We're often talking about vectors with hundreds, sometimes thousands of dimensions. Try picturing a space with 1,000 axes. It's just beyond our everyday intuition.
Yeah, my brain hurts just thinking about it.
Hmm.
What are the practical implications? What challenges does this high dimensionality create?
Well, firstly, it demands significant computational resources and memory. Just storing and processing these huge vectors takes a lot of power. Calculating the distance between 2 points in a 1,000-dimensional space involves way more computation than in our familiar 3D world.
Makes sense. More numbers to crunch.
Exactly. Secondly, we run into something called the curse of dimensionality.
The curse of dimensionality. It sounds ominous.
It is a significant challenge in practice. Basically, as you add more dimensions to a space, the volume of that space just explodes exponentially.
Okay.
Which means that even if you have a lot of data points, they tend to become very sparse. Everything starts to look kind of equidistant from everything else.
It's harder to tell what's actually close.
Exactly. In this high-dimensional, sparse environment, traditional distance-based search algorithms become much less effective at distinguishing truly similar items. Think of it like trying to find a specific star. If you only look at brightness, one dimension, lots might seem similar. Add color, distance, spectral type, more dimensions, it gets easier. But if you add too many irrelevant dimensions, they just add noise and make it harder to see the meaningful differences. The curse makes finding the newest neighbors much harder computationally.
That makes intuitive sense. So how do we fight this curse? What strategies are there to handle this high dimensionality?
Well, one main approach is dimensionality reduction. Techniques like principal component analysis, PCA, TSNE, autoencoders, even using convolutional layers. They can take these high-dimensional vectors and sort of compress them into lower-dimensional versions.
Okay, squish them down.
Kind of, yeah. While trying to keep as much of the crucial semantic information as possible, it's like distilling the essence of a complex perfume into a more concentrated form, trying to capture the most important directions of variation in the data more compactly.
But does that lose information?
That's the fundamental trade-off. By reducing dimensions, you might inevitably lose some of the finer nuances, some details captured in the original high-dimensional vector.
Which could hurt search accuracy.
It could, potentially. There's always a balance. Another family of techniques, which we'll get into more when we talk about indexing, focuses on efficiently compressing the vectors themselves, maybe without reducing the number of dimensions directly. Product quantization is a key example there.
Okay, PQ. We'll come back to that.
Yeah. This whole issue effectively managing and searching these high-dimensional vectors, that's precisely why vector databases have these specialized architectures and algorithms.
Got it. Okay, so we now have our potentially high-dimensional vectors. How do vector databases actually organize and operate on them?
Well, fundamentally, they're designed to handle these numerical representations natively. They store the vector embeddings, and crucially, they typically keep a link back to the original source data, the text document, the image file, whatever it was.
Because you need the original thing, not just the vector.
Exactly. When you do a similarity search, you want the similar item, not just its vector representation.
And how are they built? Or are they all the same?
No, there are different architectural approaches. Some are purpose-built, designed from the ground up just for vectors. Others are like extensions or integrations into existing databases. You mentioned PostgreSQL pgvector is a popular extension for that. Some document databases are adding native vector support too. And then there are architectures that actually separate the storage of the original data from the specialized vector storage and search mechanisms, like Oracle's approach.
But the common thread is that they all natively store vectors and can operate based on their geometry.
Mhm.
They don't just treat them as like data blobs.
Correct. That's the core capability. And the central operation, the engine of a vector database, is this vector similarity search. Like we said, finding the vectors that are closest or most similar to a given query vector.
Finding the k nearest neighbors, KNN.
Exactly, KNN, where K is just the number of neighbors you want back. So if you input a query vector for, say, melancholy jazz music.
The database searches for the k vectors nearest to it in the space,
Hmm.
hopefully finding sad jazz tracks.
That's the idea. Now, how do we actually measure closeness? That's where distance metrics come in.
Okay, metrics.
Several key ones are common. One of the most prevalent is cosine similarity, or its counterpart, cosine distance.
Cosine, like from high school trig.
Exactly that. It measures the cosine of the angle between two vectors. What's really valuable about cosine similarity is it focuses purely on the orientation or direction of the vectors. It ignores their magnitude, their length.
So it tells you how much two vectors are pointing in the same conceptual direction.
Precisely. The similarity score goes from -1 to +1. +1 means identical direction. 0 means unrelated direction. -1 means opposite directions. Cosine distance is often just calculated as 1 minus the similarity, giving a range of 0 to 2, where 0 means most similar.
And why is ignoring magnitude useful?
It's especially good for text analysis. Documents can be really different lengths, right? But the relative frequency and importance of terms, the conceptual direction, might be very similar. Cosine captures that well.
Okay, that makes sense. What's another common metric?
Another very intuitive one is Euclidean distance, also called L2 distance.
L2.
Yeah. It's simply the straight line distance between the endpoints of the two vectors in that multidimensional space, like measuring with a ruler.
Okay, standard distance.
Right. But unlike cosine, Euclidean distance is sensitive to the magnitude or length of the vectors. Smaller Euclidean distance means greater similarity.
So closer points are more similar.
Exactly. And for efficiency, databases often use the squared Euclidean distance. It avoids doing the square root calculation, which is slow, but it keeps the relative ordering of distances the same.
Got it. So cosine focuses on angle, direction. Euclidean focuses on straight line distance, including magnitude, any others.
We also see the dot product or inner product sometimes. You calculate it by multiplying the corresponding numbers in the two vectors and summing up the results.
Okay.
Mathematically, it's related to both the angle and the magnitudes. Generally, a higher dot product suggests greater similarity, especially if the vectors have been normalized,
Normalized, meaning...
scaled so they all have a length of 1 unit length.
Okay, so with all these options, cosine, Euclidean, dot product, how do you choose the right one?
That's a really critical choice. Best practice is usually to use the distance metric that your embedding model was trained or optimized for.
Match the model.
Yeah. If the model was designed so that cosine similarity best captures semantic relatedness in its output vectors, then that's probably your best bet for search.
Okay.
Also, consider normalization. If all your vectors are normalized to length 1, then cosine similarity, Euclidean distance, and dot product often end up giving you the same relative ranking of neighbors anyway.
Interesting.
If they're not normalized, then cosine distance or Euclidean distance are usually more robust choices. Depends if you care more about the conceptual direction, cosine, or the overall position and magnitude, Euclidean. If you're unsure, cosine distance is often a pretty good default because it handles variations in vector length naturally.
Okay, good rule of thumb.
Yeah.
So we have our vectors. We know how to measure similarity. But now, the huge challenge, how do we efficiently search through potentially billions of these high-dimensional vectors? Just calculating the distance between the query and every single vector in the database sounds incredibly slow.
You've absolutely nailed the major scalability bottleneck. Doing an exact nearest neighbor search, a true KNN search, by comparing your query against every single vector, it's computationally infeasible for large high-dimensional data sets. It just wouldn't scale for any real-world application.
So that's impossible in practice for big data sets.
Pretty much. And this is where approximate nearest neighbor, or ANN search algorithms, are the heroes.
Approximate. So we're giving up on finding the absolute mathematically perfect closest matches.
That's the fundamental trade-off, yes. ANN algorithms prioritize speed and scalability over absolute precision. The goal is to quickly find points that are highly likely to be among the true nearest neighbors, or at least extremely close to them.
So good enough, but much, much faster.
Exactly. This approximation lets us get dramatically faster search times, often achieving sublinear time complexity, which makes similarity search actually viable on massive data sets.
And how do they achieve that speed?
The key is using specialized data structures called vector indexes. Think of it like the difference between manually searching every book in a huge library versus using a well-organized card catalog or, a digital search engine.
Of vector indexes.
Okay.
How do they work? What do they do?
There's sophisticated ways to organize the high-dimensional vector data. They arrange it so that the search algorithm can rapidly prune the search space, basically, ignore huge chunks of vectors that are unlikely to be relevant, avoiding that brute force comparison against everything.
Like creating shortcuts through the data.
Yeah, exactly. Like shortcuts or guideposts in that high-dimensional space, pointing the search towards the most promising regions.
So instead of checking every item in a massive warehouse, you can quickly focus on the most relevant aisles or sections.
Perfect analogy. And there are several main families of ANN techniques used to build these indexes. You have graph-based methods, where you build a network connecting similar vectors, and the search navigates this network. You have partition-based methods,
Dividing things up.
right, dividing the vector space into smaller regions or clusters, and the search only looks in the relevant partitions. And then there are vector compression or quantization methods.
Like the PQ you mentioned.
Exactly, like product quantization. These represent vectors more compactly to speed up distance calculations and save memory.
Can you give me a concrete example, maybe one of the graph-based ones?
Sure. A really effective and widely used graph-based method is called Hierarchical Navigable Small World, or HNSW.
HNSW.
Okay. Imagine you're trying to find a specific address in a big, unfamiliar city. An HNSW index is like creating a multi-layered map.
Multi-layered.
Yeah. The top layer is very sparse, maybe just showing major highways and landmarks, letting you quickly zoom into the general area of your target.
Like an overview map.
Exactly. As you move down to the lower layers, the map gets progressively denser. More streets, more local details, allowing for really precise navigation right to the exact address.
So search starts high level, finds the general area of similar vectors, and then drills down through more detailed layers.
Precisely. The search algorithm greedily moves through this graph, always going to the neighbor that's closest to the query vector in the current layer until it finds a local minimum. Then it drops down to the next more detailed layer and repeats the process.
That sounds efficient.
It's remarkably efficient. This hierarchical structure, combined with the small world property of the graph, the idea that there are relatively short paths between any 2 points, makes the search super fast. HNSW is used in many top vector databases and libraries like Phase, Pinetone, Meviate. It's really common.
That analogy makes it much clearer. Okay, what about an example of a partition-based method, dividing the space up?
A classic one there is the inverted file index, or IVF.
IVF.
Think of organizing a huge library, not just alphabetically, but first by broad subject categories like history, science, fiction.
Right.
IVF works kind of like that. It partitions your vector space into a set number of clusters, like those subject categories, using an algorithm like co-means clustering. Each cluster gets a representative center point, a centroid.
Okay.
When you add a vector to the index, you figure out which cluster centroid it's closest to and assign it to that cluster. Then, when you search...
You don't search everything.
Right. You first compare your query vector just to the centroids of all the clusters, find the closest centroid, and then you only search thoroughly within that one cluster, or maybe the few closest ones.
So drastically cuts down the number of vectors you need to compare directly.
Exactly. It's a two-stage process. Coarse search using centroids to find the right partitions, then a finer search within those smaller subsets.
Makes sense? Narrowing it down.
Yeah. Now, IVF is often combined with that compression technique we mentioned, product quantization, or PQ.
IVF PQ?
Yep, IVF PQ. Imagine each of your long, high-dimensional vectors is like a really long password. PQ breaks that password into smaller chunks or segments.
Okay.
For each segment position, it figures out a small set of representative subvectors, creates these little code books. Then your original vector gets approximated by just storing the ID of the nearest representative subvector from the code book for each segment.
So you store codes instead of the full subvectors.
Exactly. It allows for much more compact storage, saving a lot of memory. And it speeds up distance calculations because you can estimate distances just by using these short codes and the code books, which is faster than using the full original vectors.
Wow. So IVF helps you find the right section of the library, and PQ helps you quickly scan the books in that section using a compressed description.
That's an excellent way to put it, yeah. And you can even combine HNSW with HNSW-PQ.
Yeah.
You apply the PQ compression to the vector stored within the HNSW graph structure. That reduces memory use while keeping a lot of the HNSW speed.
Okay, lots of combinations. Are there other techniques too?
There are. You have tree-based indexes like ANOY, which uses binary trees to recursively chop up the vector space, and hashing-based indexes like LSH, locality-sensitive hashing.
LSH.
Yeah, the idea there is to use special hash functions so that similar vectors are more likely to end up in the same hash bucket. Then you only search within buckets that match the query's hash.
Different strategies to narrow the search.
Exactly. And then, of course, there's the flat index you mentioned earlier. No special structure.
The brute force one.
Right. Stores the raw vectors, compares your query to every single one, guarantees you find the exact nearest neighbors.
But it's slow.
Very slow for large datasets. You might use it for tiny datasets or maybe as a benchmark to see how accurate your ANN method is. What's the recall compared to perfect?
Recall meaning how many of the true nearest neighbors it finds.
Exactly. And you also hear terms like IVF flat or HNSW flat. That just means you use the IVF partitioning or the HNSW graph navigation to narrow things down initially, but then you do an exact brute force comparison using the raw vectors within the selected clusters or graph nodes without the PQ compression approximation step.
Okay, so still faster than pure flat, but more accurate than IVF PQ or HNSW PQ.
Generally, yes. It's another point on the spectrum of trade-offs.
Right. With all these different indexing strategies, HNSW, IVF, PQ, flat combinations, how do you decide which one is best for your specific application? It seems complicated.
It boils down to those crucial trade-offs: search speed versus accuracy or recall versus resource costs, memory usage, sometimes build time too.
The classic trade-offs.
Always. Algorithms like HNSW often give you great speed and high recall, but they can use a lot of memory.
Okay.
IVF can be very fast, and its accuracy is tunable. You can decide how many clusters to search. PQ is fantastic for saving memory, but might sacrifice a bit of recall compared to flat or HNSW. Flat gives perfect recall, but is slow.
So it really depends on what you need most.
Absolutely. What are the requirements of your use case? Is super low latency critical? How vital is finding the absolute closest neighbors? Do you have tight memory constraints? Many algorithms also have tunable parameters like fsearch and HNSW or nprobe and IVF that let you fine-tune this balance between speed and accuracy yourself.
It sounds like picking the right index is a mix of understanding the tech and knowing your practical needs.
Precisely. And understanding these trade-offs is especially vital for RE-reduced systems.
Why specifically for REG?
Because you need to retrieve relevant context quickly enough for a good user experience, right?
Yeah.
But if your retrieval isn't accurate enough, if you have low recall and feed irrelevant stuff to the LLM,
It could actually make the answer worse.
exactly. It can confuse the LLM, degrade the quality, maybe even cause more hallucination. You really need high recall of truly relevant information for RE to work well. We put together a summary table comparing these index types. Maybe that helps visualize the trade-offs.
Oh, great. Let's see. Pause to mentally review table. Yeah, that table is incredibly helpful. Flat, perfect recall, slow, high memory. HNSW, very fast, very high recall, but high memory. IVF, PQ, and XC, very fast, low memory, but maybe slightly less recall. HNSW-NW, a compromise on memory compared to pure HNSW. Really lays out the choices.
Right. It highlights those key decision points.
Okay, so we've built our vector database, filled it with embeddings, picked and built an efficient index. Now let's really connect this back to retrieval augmented generation systems. How does this infrastructure actually enable RAG?
Okay, so remember, we said large language models have limitations. Their knowledge is static, can be outdated, inaccurate, lack specific details.
Right, the encyclopedia that can't be updated.
Exactly. RAG is designed specifically to fix that by giving the LLM access to external current knowledge right when it's generating a response. It's like giving that brilliant but sometimes forgetful genius access to a perfect, always updated research library right when they need it.
So instead of just relying on what's baked in from training, they can look things up on the fly,
Yeah.
essentially.
Essentially, yes. RAG works by first retrieving relevant pieces of information from an external knowledge source before the LLM generates its answer.
Okay, retrieval first.
Yeah. This retrieved context provides grounding, evidence. It leads to more accurate, timely, contextually appropriate outputs. Plus, it lets us use specialized knowledge company data, recent research, without the massive cost and time of retraining or fine-tuning the whole LLM. RAG basically provides a dynamic, specific, long-term memory for these models.
And the vector database is that memory's access mechanism.
Precisely. The vector database, with its fast semantic search, is the key component for efficiently accessing that external knowledge. Within the RAG architecture, the vector database serves as the external knowledge repository, or the non-parametric memory. Its main job is rapid, semantically relevant retrieval.
Okay, so how does the knowledge actually get into the vector database for a RAG system? What's that setup process?
That involves a process often called indexing, or data hydration. First step, gather your knowledge documents. This could be anything: web pages, PDFs, Word docs, internal wikis, support tickets.
Your corpus of knowledge.
Exactly. Next, these documents usually need to be broken down into smaller, manageable units called chunks.
Chunking, why is that important?
It's critical. How you chunk, by paragraph, by sentence, fixed size, maybe using more clever semantic chunking, massively impacts the relevance of what gets retrieved later. Too big chunks might contain irrelevant info. Too small might lack context.
Ah, okay. Finding the right granularity.
Right. Once you have your chunks, you use an appropriate embedding model, the same kind we discussed earlier, to turn each chunk into a high-dimensional vector embedding.
Embedding the chunks.
Yep. Finally, these embeddings are stored in your vector database, usually linked back to the original text chunk they came from, and then you build that efficient ANN index, HNSW, IVF, PQ, whatever you chose, over these embeddings to make the search fast.
Okay, so the knowledge is prepped, vectorized, indexed, ready to go. Now, what happens when a user actually asks the RAG system a question? Walk me through that flow.
Right, this is the RAG's workflow at inference time when it's actually answering. The user submits their query, first step. That query itself gets converted into a vector embedding.
Using the exact same embedding model.
Absolutely critical. You must use the identical embedding model that you used for your knowledge corpus. Otherwise, the query and the knowledge won't be speaking the same semantic language. They won't be comparable in the vector space.
Makes perfect sense. Same language needed. Okay, query embedded. Then what?
Then, that query vector is sent to the vector database. The database uses its pre-built ANN index and the chosen distance metric, like cosine similarity, to perform a similarity search across all the stored chunk embeddings. It finds the top k most semantically similar chunk vectors.
So the k closest chunks conceptually to the question.
Exactly. K is tunable. Maybe you want the top 3, top 5 chunks. Once those top k embeddings are found, this system retrieves the actual text chunks that correspond to them.
Gets the original text for those best matches.
Right. These retrieved chunks are the external knowledge the system thinks is most relevant to the query.
And what happens to these retrieved snippets? They don't just get shown to the user, right?
No, this is where the augmented generation part kicks in. The retrieved text chunks are combined with the original user query to create an augmented prompt.
Augmented prompt.
Yeah. This usually involves some clever prompt engineering, structuring the prompt to tell the LLM how to best use the provided context. You might stick the context before the query, after it, format it clearly. The goal is to guide the LLM. Okay, here's the question and here's some relevant information. Use this information to formulate your answer.
So you're explicitly giving the LLM the raw material and instructions to build a better grounded answer.
Precisely. This augmented prompt is then fed into the LLM. The LLM processes the whole thing, the original question, plus the retrieved context, and generates the final response. And the hope, the design, is that this response will be grounded in that retrieved context, making it more accurate, relevant, and less likely to just make stuff up.
Yeah, it sounds like a really powerful approach.
Yeah.
But it also seems like there are quite a few places things could go wrong. What if the retrieval step messes up?
You're absolutely right to ask that. The overall effectiveness of our RAG hinges heavily on the quality of that retrieval step.
Yeah.
If the vector database pulls back irrelevant chunks, or maybe inaccurate ones,
Yeah.
maybe because the embeddings weren't great, or the metric was wrong, or the index wasn't tuned well, then feeding that bad context into the LLM can actually confuse it. It can degrade the final output quality, maybe even make things worse.
A bad retrieval can poison the well for the LLM.
Exactly. And there are other challenges, too. LLMs sometimes struggle with really long contexts. They might forget information in the middle, the loss in the middle problem, or there might just be a semantic gap. What the retriever thinks is similar isn't quite how the LLM reasons about it. Or the retrieved info might even contradict the LLM's internal knowledge, creating conflicts.
So building a good RGOG system isn't just plug and play. It's not just slapping a vector database onto an LLM.
Not at all. It requires careful tuning and optimization. That's why there's so much ongoing research and development in improving this whole retrieval generation interface.
Like what kind of things?
Things like improving the quality and chunking of the source data itself, better indexing strategies, maybe transforming or rewriting the user's query before retrieval to make it more effective.
Ah, query transformation.
Yeah. Or post-retrieval processing, like re-ranking the retrieved chunks, filtering out less relevant ones before sending them to the LLM, maybe even summarizing them first,
Re-ranking and filtering.
and exploring ways to fuse the retrieved info more tightly with the LLM's generation process. Techniques like adaptive RAG, where the system decides if and what to retrieve based on the query, or even fine-tuning the retriever and the generator together so they work better as a team. These are all active research areas.
It sounds like a field that's moving really fast, getting more sophisticated all the time. But when you do get it right, when a RAG system is well designed, the benefits must be pretty significant.
Oh, absolutely. A well-functioning ARG system powered by a good vector database offers major advantages. First, accuracy. It significantly improves accuracy and reduces those LLM hallucinations by grounding responses in actual evidence.
That's huge.
It is. Second, it gives LLMs access to current information and specific domain knowledge without needing costly retraining. You just update the vector database.
Much cheaper and faster.
Way cheaper, way faster. Third, ARG systems can potentially provide citations point back to the source documents they used, which increases transparency and trust.
You can see where the answer came from.
Exactly. And finally, it gives developers much more control over the knowledge sources the AI is actually using.
So vector databases really are fundamental infrastructure for making LLMs more practical, reliable, knowledgeable, grounded.
They really are. They've kind of moved from being a niche technology to being a critical piece of the modern AI puzzle, especially with a RAG taking off like it has. They provide that fast, semantically smart memory that lets LLMs tap into vast amounts of unstructured knowledge effectively.
Okay, so just to recap our deep dive then. We've seen that vector databases are these specialized systems built for storing and searching high-dimensional vector embeddings.
Which capture the meaning of unstructured data.
Right. They use clever indexing methods like HNSW and IVFPQ for rapid approximate nearest neighbor search, using distance metrics like cosine similarity or Euclidean distance.
Finding conceptually similar items quickly.
And crucially, they act as the essential external knowledge store, the memory, for retrieval augmented generation systems, feeding LLMs the context they need to generate better, more accurate, more reliable answers.
Well summarized. And it's worth remembering, their impact goes way beyond just RAG.
Oh, yeah.
Definitely. That core ability, fast semantic similarity search, is incredibly valuable for tons of applications. Building smarter search engines, better recommendation systems, improving fraud detection, powering computer vision tasks, even speeding up research in areas like bioinformatics.
So they're becoming foundational across AI.
Their importance in the AI landscape is just growing and growing.
It's fascinating to think where this is all heading. We're seeing constant improvements in the ANN algorithms themselves, better ways to handle data that changes all the time, progress in multimodal searching across text, images, audio seamlessly, and like you said, huge efforts in optimizing that whole RAG loop, query rewriting, adaptive retrieval, post-retrieval processing, maybe tighter integration between the retriever and the generator, how to handle noisy or conflicting information.
Absolutely. There's this really powerful synergy happening. On one hand, we're getting better and better embedding models that capture meaning with more nuance and complexity.
Right.
And on the other hand, we're getting vector databases that can store and search these richer representations faster and more efficiently.
That interplay is driving things forward.
It really is. It's a key driver pushing AI towards being more knowledgeable, more accurate, and ultimately more grounded in the messy reality of the world. It really makes you wonder, doesn't it? What other transformative possibilities will emerge as these technologies keep maturing and weaving themselves even more deeply into our digital lives?